Hello, and welcome to this explainer. I am so thrilled you're here today because we are tackling one of the most fascinating, mind-bending shifts happening right now in artificial intelligence. If you've been using ChatGPT lately and noticed it suddenly pausing to, actually think before it answers you, well, that is exactly what we're looking at today. We are going to break down the actual mechanics behind this, relying entirely on a groundbreaking new research paper that maps out exactly how AI models think when they're given more time. We've got a highly structured journey ahead, so let's just jump right in.
So, here is the central question we are exploring today. What actually happens under the hood when we give an AI more time to think? In the early days, right, you'd ask an AI question and it would instantly spit out an answer, just predicting one word at a time. But now we're seeing systems that pause, they output these long chains of intermediate thoughts, and they consume significantly more computing power before giving you a final response. But what is the machine literally doing with all that extra time? It is wild how fast this landscape has evolved. Back in 2021 and 2022, reasoning was mostly just a prompting trick. We literally just asked models to think step by step to get a single chain of thought. But heading into 2025 and 2026, we've moved from simple prompting to incredibly complex, budget-aware search algorithms. Modern AI doesn't just generate a single path anymore. It actively allocates compute, searches through possible answers, and dynamically controls its own reasoning budget. It's a massive paradigm shift. Which leads us to a massive headache in the AI community right now. Why are AI benchmarks suddenly so confusing to read? You might see two different companies claiming their AI is the absolute smartest, but their numbers just do not match up. The reason? Test time scaling, which basically just means giving the AI more compute at inference time, has become a seriously overloaded buzzword. It's being used as a catch-all term for vastly different underlying algorithms. Comparing them as if they're the exact same thing is creating huge evaluation headaches. To clear up this confusion, we're going to use a strict taxonomy from the researchers as our roadmap today. 1. The test time scaling problem. 2. 3 regimes of reasoning. 3. Decoding the AI choices. 4. Evaluating the full system. And 5. A massive data release. Section 1. The test time scaling problem. Unpacking the overloaded buzzword.
The absolutely crucial thing to understand here is that giving an AI extra compute isn't just one magic trick. You can't just throw raw processing power at a model and expect it to automatically get smarter. We need a precise vocabulary. The researchers formally defined test time scaling as a budgeted algorithm built on top of a fixed autoregressive model, which is simply a model that predicts one word at a time. Let's visualize this. Imagine every possible word the AI could say as a branching path. The AI's potential reasoning represents the branches of a massive invisible tree. Test time scaling just describes the different strategies an algorithm uses to spend its budget, exploring the branches of this tree before deciding on the final path.
Section 2. 3 regimes of reasoning. A structural taxonomy. If exploring this giant tree of thoughts is the goal, how exactly do different AIs actually do it? Well, the researchers chunked this highly complex computer science into 3 distinct structural buckets, or regimes. Here is the first regime, single trajectory sequential scaling. In this approach, all the extra compute budget is focused entirely on a single evolving response. There are no competing, parallel ideas being tested at all. The AI just keeps pushing forward on one line of thought. The big advantage here? Low orchestration overhead. But the major catch is that if the AI makes a mistake early on, there are no backup plans. It has to explicitly realize it messed up and self-revise along that exact same path to recover.
The second regime is leaf-level scaling. Instead of betting everything on just one path, the AI uses its compute budget to explore multiple different paths all the way to the very end, to the leaves of the tree. Only after multiple completed candidate answers are generated does the system look at all of them and use a verifier, or a voting system, to pick the winner. It is fantastic for generating a wide variety of ideas, but it has a flaw. It is highly susceptible to reward hacking. That's where the system might pick a response that looks good to the automated judge, but is actually fundamentally flawed.
And the third regime is prefix-level scaling. In this regime, the AI evaluates partial, unfinished thoughts. It uses its budget to expand promising ideas and mercilessly prune the bad ones early on. This is incredibly efficient for utilizing a compute budget. But there's a serious risk here. If the algorithm misjudges a partial thought and prunes it too early, it permanently eliminates that branch. If that pruned branch actually held the correct answer, the AI can never recover it. Let's quickly summarize these regimes because your compute allocation totally dictates your pros and cons. Single trajectory is low overhead but relies entirely on self-revision. Leaf level gives you great coverage of different fully formed ideas, but you risk over-optimizing for the final judge. And prefix level is super efficient at using the budget as you go, but early printing can accidentally kill off the right answer forever. So the next time a company says their AI uses test time scaling, you now know you need to ask, wait, which of these three regimes are you actually using?
Section 3. Decoding the AI choices, the granular pipeline.
Now that we understand the macro view of the tree, let's zoom way into the micro view. How is a single word, a token, actually chosen by the AI's decoder inside these trees? The researchers broke this down into a highly granular, lightning-fast pipeline. Step 1 happens in an instant. The system gathers its prefix local inputs. This includes the prompt you gave it, the words it has already generated, and all of its current internal hidden states. It is essentially taking stock of exactly where it is in the conversation. Instantly after that, we hit step 2, measure construction. Think of this like a chef weighing ingredients. Based on the context it just gathered, the decoder assigns mathematical weights to all the possible next tokens in its entire vocabulary. It's scoring every possible word it knows based on how likely it is to logically come next. Next comes step 3, support construction. This acts basically like a bouncer at a door. The AI doesn't actually want to consider every single word in the dictionary. It only wants the most logical ones. This gate restricts the list, throwing out the wildly improbable words, and strictly limiting which tokens actually remain eligible for the AI to choose from. Then we hit step 4, the energy gate interface. Because we just tossed out a bunch of improbable words, the mathematical probabilities of the words we kept don't add up to 100% anymore. This interface steps in to renormalize the options, essentially recalculating the pie chart so the remaining probabilities equal 100% again, locking in the final adjusted numbers for only our retained candidates. And finally, step 5. Based on those newly renormalized probabilities, the final token decision is made, and a word appears. So the really crucial takeaway here is that when an AI generates a response, it isn't magic. It is running this exact 5-step granular pipeline, over and over, thousands of times a minute, strictly governed by the rules of whichever structural tree regime it's operating inside of.
Section 4. Evaluating the full system. A new standard.
Because if the process is literally this complex, how in the world are researchers supposed to fairly evaluate if one AI model is actually better than another? Well, the paper argues we desperately need a totally new standard. Historically, we just evaluated an AI based on its base model weights, essentially its core brain. But today, you cannot evaluate the brain in isolation. You have to evaluate the complete inference protocol. That means testing the exact prompt template, the specific decoder settings, the search controller mapping the tree, the logic used to reduce final answers, the external judge model, and the hard limits on budget and stopping rules. If a company claims a high benchmark score but doesn't disclose this entire list, the score is practically meaningless because any single one of these levers can drastically alter the final performance. To prove this, the researchers cleanly contrast two different ways to run evaluations. A shared bank comparison takes a fixed set of already completed answers and only tests how good the AI's final selection logic is at picking the best one. But an end-to-end evaluation measures the complete dynamic system, from generating the very first word to the causal stopping rule that cuts off the compute budget. This perfectly illustrates why reporting exact compute metrics alongside accuracy is absolutely non-negotiable now. You could easily have a model that looks like a total genius in a shared bank test, but completely fails in end-to-end because it just doesn't know how to efficiently budget its own search. Section 5, a massive data release fueling the open source ecosystem. The researchers didn't just point out these problems, they provided a massive solution to help the entire AI community build better reasoning systems. And that solution is scaled to the tune of over 2 billion. No, that is not a typo. The researchers have assembled and released over 2 billion full reasoning traces across complex domains like science, reasoning, and competition mathematics. This staggering amount of data is completely open source, hosted right now on Hugging Face. Why does this matter to you and the broader ecosystem? Because this massive dataset provides the progressively richer, token-level signals that developers desperately need. By analyzing these 2 billion traces, developers can train much smarter verifiers and judges. They can finally conduct real, reproducible studies comparing those different search regimes we talked about earlier, ultimately empowering the open-weight ecosystem to actually compete with proprietary closed systems. So, we end with this provocative thought.
We now know exactly how test time scaling works across single trajectory, leaf level, and prefix level trees. We know the exact granular pipeline for how tokens are selected, and we know the rigorous system-level evaluations required to prove they actually work. With a 2 billion trace roadmap now entirely open source and freely available, what will the AI community build next? The branches of possibility are quite literally endless. Thank you so much for joining me on this explainer, and keep learning.